And let me push the record, and it's time to start. Hope more people will get inside our Zoom event soon. Welcome everyone to our tonight's event, Introduction to 3D Computer Vision, with Deniz, who is an engineer working at Preferred Networks, a company that everyone who lives in Japan and works in tech knows very well. Thanks for coming, Deniz. It's a pleasure for us. Before we move on to the main content of our event, I would just like to give a couple of words about our community, what we are doing here, why we are having this event. For those who don't know, my name is Sasha. I'm in charge of partnerships and events at Wagon Tokyo, a global coding bootcamp. We originally from France, Paris, and we have 40 campuses around the world with 10,000 graduates. What we do, we teach people how to code, how to build web applications from scratch during our web development bootcamps, and also how to analyze and manipulate data during our data science bootcamp. And deep learning is something that we also teach at our bootcamp. So I expect people from our community will definitely appreciate what we're having today. And so aside from the coding bootcamps, we also run events like this, weekly free online workshops and tech talks, where we invite amazing speakers like Deniz to share their expertise and knowledge with our community, because we want our community to learn more and grow. Cool. Maybe just the last word, if you guys have any questions about Wagon community, coding bootcamps, or if you would like to visit our campus in Meguro, 5 minutes walk from Meguro station, feel free to send me a message. Cool. And without ado, I would like to give a microphone to Deniz. Deniz, please go ahead. The stage is yours. Just one small notion. So Deniz will have a presentation and you won't be able to see the screen, the chat all the time. So if you guys have any questions, please write down your questions in the chat and we will read them between their chapters in Deniz presentations when we have break. And Deniz, the time is yours. Please go ahead.
Thank you a lot, Sasha. Thank you a lot. So hello, everyone. My name is Deniz, and let me share my screen first. So I hope you can see my screen.
Yep.
Great. So my name is Deniz, and today I'm actually in my vacation, and I'm joining the event from Turkey, from my home. So I hope there's no connection problem. So today's agenda is I will be having some small introduction about myself and about my company, Preferred Networks, and we will be discussing about what is 3D computer vision, what is differential rendering, which is actually an emerging topic in this area. And I will briefly explain how the differential rendering works, and I will present to you one of our application that we did by using the differential rendering. And I will show you present you some other examples, and I will have some time for open discussion. So about myself, I have graduated from my master's degree in Turkey in 2014. And as soon as I graduated, I moved to Japan within a few months, and I started work in the face recognition areas. And then I switched to medical imaging and developing the algorithms for medical imaging. And since 2018, I'm working in Preferred Networks as an engineer, and I was also an engineering manager for a while, especially for the 3D computer vision in Preferred Networks. And also I have completed some projects using the 3D computer vision and cloud gaming purposes. And the Preferred Networks, some people in Japan may have already know about it, but it is founded, we have founded in March 2014, and we are mainly located, our HQ is located in Tokyo, and we also have a branch office in California. And we have more than 270 and maybe 300 engineers and researchers. And this is a very engineering and researcher-oriented company, so that we don't have much salesperson or any different titles. So mainly nearly everyone in the company is either engineer or researcher, independent from the seniority. So, and we also deal with many different areas, including manufacturing, logistic, transportation, especially with the collaboration with Toyota or biohealth and healthcare. And you may have seen our personal robots 2 years before in CTEC, and some manga colorization projects are ongoing. And briefly, we have won the Green 500 list by using our super computer, which was nominated as the most efficient supercomputer in the Green 500 list. And we have been receiving many different awards from the Japanese government or internationally so far. So let's discuss about what is 3D computer vision so far. So you may have encountered with sequential data in life, like average temperature or temperature over time, or like electricity consumption, or those kind of 1D data, or text can also be assumed as a one-dimensional data. And there are also some images which can be accepted as a two-dimensional data. So the purpose of the 3D computer vision is directly working with the 3D data, or somehow transfer the 2D knowledge into 3D and operate in the 3D. So some of the examples of that application is the 3D perception, for example, directly taking the point clouds and trying to predict where are the cars in those 3D point clouds. Or again, taking some point cloud and defining, is this a mug table, the object classification in 3D, or segmenting some parts, or detecting the shapes of the objects. Or if you have a noisy point clouds, you can train some networks to complete the noises and filter all the noises so that you can get the much better shape. There are many different applications that I couldn't fit into this slide, and I will be mentioning about them briefly. So about mentioning about the differential rendering, I think at first we need to understand the supervised deep learning pipeline so far. So in the supervised deep learning pipeline, we get input data, whatever it is, 3D, 2D, 1D, independent from the dimensionality. We apply a forward pass, and it gives us a decision. Is it 1 or 0 or multi-class classification, or many different applications? It's just a simplicity. And we get some labels. We label them previously. We calculate the error. Seems like how much error the network predicted. And then we backpropagate all the loss by penalizing all the neurons within the network model. And we reiterate over it tens of thousands of times so that the network can learn how to generalize a prediction giving an input image. This is great if you have the labels. However, whenever you work in the 3D computer vision, different from the 1D or 2D, there are different problems that arises. One of them is it is really costly to collect the 3D data, because most likely you have to equip Lidar-like equipments for precise data collection. Else, there are really significant errors and noises in the collected data, and it actually prevents you to create a good ground truths while training a model. And the second thing is, it is really not easy to label the 3D data accurately. For example, if you have an image and if you want to label where the objects are, you only need to click 4 points or even fewer points on the image, and you can slightly adjust if you make a mistake. However, if it's a 3D data, if it's a volume, it is really becoming a much harder problem to label it precisely. And actually, it is an open problem for human-computer interaction area. So that's another challenge that we face whenever we mention about the 3D computer vision. And sometimes it is really impossible to generate the 3D labels. For example, if you take some images in the wild, like you take your phone and you start to take the images in the streets, most likely you won't be able to distinguish where the lights are coming, how many lights there are in the scene, and how they are interfering with each other. It is quite impossible for a human to annotate all of those information from the images. It can only be done in a controlled environment, but not in the wild. However, our world and most of the information that we want to extract, analyze both 3D and in the wild. So differential rendering provides a solution to those problems. So what it does is, we know the rendering operation. I will make briefly mention about it. It just adds a differentiation operation to the rendering, so that we can add it to the neural network so that the backpropagation can occur by following the images. So basically, it allows us to create a projective geometry-aware dimensional reduction from 3D to 2D. It allows us to use 2D images for 3D supervision without we don't need to annotate 3D anymore. We can just annotate the 2D images and we can just apply differential rendering technique through it. And this is the main advantage of it. In the image, you'll see the general common pipeline for us to be able to use how to use the differential renderer. Actually, it also helps us to decompose an image into 3D scene objects like materials, lights, where are the cameras, what is the geometry of the objects. And just by rendering, we know that it should be the same as the input observation so that we can create a self-supervision loop which actually eliminates all the requirements of the supervision and annotation. So this is amazing if we can make it work, because it minimizes and makes all the annotation cost to zero. So far, am I going too fast, or is there any question?
So far, it's okay. We don't have any questions. So if you guys have anything, feel free to write down in the chat. So maybe just, when you get to some, I would say, practical approaches, something like that, we will have more questions coming from people.
Great, great. Then let me briefly introduce how the differential rendering works. So let's assume we have the RGB rendering. This is the outputs of the rendering part. So as a for reference. So the input image or input data can be a point cloud, which will be composed on the X, Y, Z coordinates of each representative part of the surface. Or it may be a mesh, which may include the triangulation and the surface information and the texture on top of the point clouds. Or it may be a voxel, similar to Minecraft-like volumes. Or we can use the implicit functions, which is a little bit more advanced representation technique. So basically, point cloud, mesh, and voxels are explicit representations, which means we literally say that this is the point, this is the XYZ point of the surface. And the implicit representation is something that we encode all the shape into the parameters of a function. I will briefly mention about them. But at first, whenever we mention about the rendering, we need to understand differential rendering. We need to understand the basic how the rendering operation works. So very briefly, the rendering operation takes the 3D mesh object or 3D explicit representation object. Then it reprojects all of the 3D meshes into the 2D screen. And it finds all the triangles in the 2D screen. It divides all of those 3D, the triangles into the cubes or like the fragments. Then it applies to the colors and we see it as an image, as an output. And optionally, it can just add more light reflection or refraction or shadow information to generate more realistic information in there. Or the previous one was called rasterization, which is super fast, much faster. Most of the games work in that way. Most of the graphics objects work in that way. And there is the more advanced technique, which is ray tracing, which is becoming quite popular through the NVIDIA's recent RTX cards. So this is actually required to use more, generate more realistic information, more realistic images. All the animations, all the 3D material rendering in the mechanical engineering are being done in that way. So basically, for each pixel, we shoot a hypothetical ray, and we follow all the reflections or refractions until it hits a light source, so that we can find what is the color of that pixel by shooting multiple rays. And this is the two main parts of the rendering operations. So whenever we mention about the rasterization, we mention about projecting to the screen space. This is differentiable. We can order and choose the visible triangles because they may overlap to each other. This is differentiable, or we don't need to apply any differentiation. This is bypassable. However, digitization, the fragment creation and rasterization is not differentiable by nature. And the rest is actually also differentiable. So whenever we try to calculate the impact of the pixel color or the mesh impact of the mesh vertex to the output pixel color, we can get no signal, so we cannot backpropagate any signal. So we cannot add the existing rendering or rasterization pipeline to a deep learning. So that's why we need to apply something. We need to differentiate the rasterization process. So to be able to differentiate the rasterization, we have two approaches to tackle. Either we need to actually do two problems. The first one is how to create the gradients for the objects, like the visible areas. And the second is how to create the gradients, we can backpropagate the signal for the background pixels. So we have two mainstream approaches. One of them is we either approximate the gradients, so we actually apply whatever the rendering process is, and we just manually calculate what are the gradients should be, or we approximate the rasterization. So this is all are actually the approximation-based methods rather than the analytical calculation. So whenever we mention about approximating the gradients in here, there are two papers published. One of them is 2014, and one of the main papers was in 2018. So this is a very novel area compared to the many other research areas. So in that regard, as you see in the blue areas, actually, if a pixel, a background pixel, it tries to stretch the triangle to match if the supervision area is in the blue area or green area. But both methods cannot provide any gradients or any signal, supervision signal for the point Pi in the image that you see. But the advantage of approximating the gradients are they provide the useful gradients because we calculate them manually. And we can use any professional rasterizer for the forward pass with small modifications. However, it is quite hard process to handcraft the gradients, and it is really time consuming to develop such a approximation. And if you need in your application the accurate gradients rather than the approximated ones, your application, this method will most likely fail. So this brings us another approach, which is approximating the forward pass. Instead of trying to choose the triangles, which triangle is visible, which one is not visible, actually, how about we just add all of them to generate the final pixel color. This is a paper published, I think, from Facebook. And instead of choosing one triangle and trying to calculate the backward pass, they just apply an approximated forward pass. The advantage is everything is calculated automatically by using the PyTorch or TensorFlow or any other deep learning framework that you want. You just write it as if a regular neural network model. And each pixel can be covered for gradient calculation. So there is no black areas or empty areas. The disadvantage is the output is quite blurry because not one triangle does not only one triangle impacts the final color, but if there are 100 triangles that may create that pixel's color, it may bring actually some noise. And this is the error in the approximation. And it is computationally quite expensive compared to the previous one. So that's why if you need a real-time application, most likely this will be quite a challenging problem to use the mesh rasterization approximation. Another approach is we can apply the point cloud rendering. There is no rasterization process. This is theoretically all the pipeline is differentiable. So we don't need to apply many other things. But there are still problems due to the discrete nature of the images. What if whenever we rasterize, whenever we project all the 3D points into a 2D plane, what if both more than one, like two or more points project to the same pixel? So in that case, how we can choose which color that the pixel will be choosing, and so that we can backpropagate, we can link to the pixel with one and only one 3D point clouds. So there are two approaches that are being done so far about that. One of them is increasing the spatial dimension, so increasing the image size, so that all the 3D points will be projected one and only one pixel, so it prevents all the problem. Then we can just apply the max pooling or mean pooling operations. And similar to the forward rendering pass, we just assign a pseudo sizing to each point, so that we then apply the same pipeline as the differentiable mesh rasterization. And there is the voxel rendering. This is also another. This work should be also from Facebook. So the ray matching should be differentiably by nature because of its discrete nature. So we can, if we use the voxel volumes, this is most of the problems are resolved because we can just follow a ray, a hypothetical ray, and we can just cumulatively add all the values to generate the final pixel points. However, the main problem to use the voxels are it has the memory consumption is extremely cubically increasing. So if you want to increase the dimension, which will impact your resolution, you will need to add more and more and more memory. You will hit to the more and more larger memory limitations. So this is great for small objects, but trying to model a whole scene like your home just by using the 3D voxels may really consume a significant amount of memory in your environments. And lastly, there's the differentiating and ray tracing may be possible. Actually, the ray tracing is by nature is differentiable too, because we follow and all the refraction and refraction of the rays are calculated in a differentiable manner. All the functions are differentiable. However, whenever one of the rays hit to the object surface, it causes a discontinuity similar to the Rayleigh operation. So that's why we need to apply some kind of approximation for that purpose too. And you may have already seen some neural rendering operations, which actually the guns are using, for example, or many 2D image generators may be using such kind of neural rendering operations. In this case, we don't write any rendering layers. We don't write any operation. It's just like a convolutional neural networks. So that's it just generates an output image from input data, whatever you define. So this is definitely much more simpler than the previous operations that I mentioned. However, it does not guarantee the geometric consistency. So if your application requires a good geometry and geometric consistency, for example, you need to see the object from multiple different angles. And if you want that all the angles are meaningfully matching, neural rendering may be failing in that kind of operations. And you need the data to learn. So basically each neural renderer will be application specific. So you have to retrain it again and again with new data for different applications. And we mentioned about implicit functions, and this will be the last representation parts. So consider the aim is to represent this circle in 3D. So if you are using the mesh or point cloud representation, you need to sample endpoints on the circle. So basically, you need at minimum m by 2 parameters to represent this circle. And still, by default, it won't be smooth. You may need to apply some post-processing filtering to smoothen to make it look like a circle. You can use the voxel. In that case, you need to create a discretization to m bins, like m by m image, and you just define is it on or off or like 1 or 0, so that you can define a circle in a voxel part. Or you can use an implicit function. In this case, you just define a function, fxy, and it will just require 3 parameters, which is significantly much lower than any other representation would be required. And you just evaluate the same function for whatever the resolution that you want, whatever the position that you want. And the implicit function will generate you if it is a circle or not. So how we can use the implicit representation, and this is a very recent technique, and this is actually caused quite a breakthrough in the last 1 year, 1 to 1.5 year. There is actually a breakthrough in the 3D computer vision in the world right now. So let's increase the complexity a bit, and let's try to represent the following 3D object as an implicit function. I really don't think that it is possible to handcraft the functions to represent the shape for such a complexity. So Sitzman, who is actually he is actually our advisor, preferred networks advisor, and he published a paper 2 years ago in which we can just take the XYZ points and which gives us the color and the geometry network. It's a very simple network, and we just need to evaluate this network for each XYZ points that we want to see if it is occupied or not occupied or what is the color. So what does it provide us? Why the implicit scene representations are quite important? At first, it just removes all the memory requirements or most of the memory requirements that Voxel will be requiring. So we can just generate infinite resolution scenes with the same number of parameters. So this is actually an amazing breakthrough for us to work through. And we define the scene as a continuous function. So all the previous explicit representations are discrete. So whenever we jump through one discrete step, actually it is one of the source of the error for us. But whenever we define it as a continuous function, we can just evaluate the function in the middle points. We don't need to operate in the discrete space. This is a great advantage if you want to increase the resolution or level of detail. And we can just embed different meta information. This is not only about occupancy. We can also embed the color. We can also embed the classes. We can also embed the instances, whichever information that you want. This is not only volume. And it actually provides us a possibility to remove expensive 3D CNNs, convolutional neural networks, to process the volume, which is more or less the de facto way to process the 3D volumes right now. So far, is there any question?
No, I don't see any questions in the chat. Either it's very clear or it's very difficult. Yeah, I mean, if we have any feedbacks from people, if everything is clear, if you want Deniz maybe to elaborate more on some particular subject, feel free to write it down in the chat. So far, so good.
Great.
Good.
So far, I guess it was more theoretical, all the details. It may sound a little bit hard. Let's jump into some kind of applications. I would like to show you one of the paper that we published last year in the European Conference of Computer Vision. And our purpose in this work was, given a monocular RGB image, so we have only one RGB image, we wanted to predict 3D dimension, texture, rotation, and location of the objects in the metric scale, not in the like the unit scale, in the metric scale as if in the real world. And we didn't want to use any supervision with zero annotation. Would it be possible? This was our question. So this is actually this was one of the really hard work for us to challenge, because it was like there is no supervision. There is very limited information that we can get. So we had to really dig into the many different approaches that we can elaborate. And in this work, actually, we used our the synthetic information, like synthetic cars, synthetic 3D objects, to be able to train or optimize for a network where for the network to be able to understand how does a car look like, how does a object look like. And we applied such knowledge to be able to find what is the object's shape and the location and dimensions in the 3D world. So this is the video that I would like to show, the optimization process. So as you see, it starts from the scratch, and over the time, within the 200 iterations, it learns how to fit a car or how to generate and fit a car, including the 3D location, rotation, and the texture for all the cars that you can see in an image. And actually, the results were quite surprising for us too, and we were really excited about receiving such kind of outputs, because it allowed us to annotate automatically all the 3D information for the cars just by looking one single image with virtually zero annotation cost. I think there have been some chats messages so far.
Yeah, so we have a question. We have a feedback from Rodrigo. He's not following quite well, and also we have a question. If possible, would like to hear your intake on the system Tesla applies for their self-driving technology?
I will. So Lidar. Yeah, as far as I know, the Lidar technology is the one that's they predict from the images. They try to predict the depth map of the image, and then they project it to the 3D, and then they apply to the 3D object detection algorithms on top of that point cloud generated from the predicted depth map. So actually, this was our work was a few level advanced compared to the pseudo lidar technology. This was definitely one of our starting points, the pseudo lidar technology, and we actually in the pseudo lidar it is somehow the sparse points that you get, because for each pixel you get only one and strictly one point clouds in the scene. However, in our application, for example, we actually process the volumes in the dense manner. So and because we trained a synthetic dense object generator, so this was one of the main difference between Tesla's so LiDAR technology and what we have done so far. However, I don't have the more detailed knowledge about their technology. I hope it replied your question. Yeah, great. And is there any other questions or comments that I'm missing?
Looks good.
Great. So I would like to show you some other examples that are being done with such technology. For example, what if you have the Kanazawa sensei, she's really famous in this area. They made a work like, what if you see only one 2D image, and would it be possible to generate the 3D shapes of the birds just by seeing the 2D image? And this was single view 3D object reconstruction, one of the early work of this area. And the similar application can also be done to find the human body pose and shape, because what we need to do is we need to get a 3D human body in the synthetic environments, and we just need to render it in the 2D part, and we want that it matches with the input image. So this technology is also used to find the human body shape, along with the hand pose estimation, and in the 3D world. Similarly, it is possible to generate the 3D faces of the people without using any supervision. Just by using the 2D image, we know the rough geometry of the faces, and then just by iterating and just by learning how to deform a base face model to match into the input image, we can actually train a network for either generative or predictive or whichever application that we want. And this is also possible to apply the style transfer in 3D. Guns are making them in 2D so far, and there have been a lot of different applications shown. But by using the differential rendering, we can apply the similar technology for 3D as a style transfer. And the breakthrough paper last year, Nerf paper, neural radiance fields. This really impacted all the 3D computer vision area quite significantly. And what do? Is the problem that they bring is, considering that you have tens or hundreds of input image that you know where the camera locations are, and you only have the image and the camera pose eventually. So would it be possible to synthesize the new views that you don't know how it would be looking like? let's say I have this view and this view, how a new image would be looking like if we had looked from the center. And would it be possible to reconstruct the 3D shape just by looking the multiple 2D images accurately? So they achieved an amazing performance, and all the moving GIFs or GIF objects that you see are reconstructed just by looking the 2D images. And this is really a fascinating outcome that we have received so far. And similarly, the Nerf is or dynamic Nerf. I think this was from the Google last year, a few months ago. So what do they do is, what if the scene is not static? Because Nerf applies the optimization process to the static objects. This is perfect, but the world is dynamic. So they applied, they evaluate or they increased the model's complexity a bit, and they added for the deformation information. So considering that if you take this, let me take my pointer. If you provide this input video that you take from very different angles, and what if you want to stabilize that? What if you want the camera to look like only from the front, without having any ego motion from the camera? And the novel view color is the output of this question. Basically, it cancels out all the movement in the backgrounds, and it stabilizes the head only in the central position. Similarly, on the right side, you can see the similar outputs, how it would be looking like. What if we stabilize the front object and we change the background? There is one more paper published. Instead of using an occupancy part, it's actually give us the sign distance function to say like how far we are away from the object surface, which is called the sign distance function. And this was one of the early work of this implicit representation, the deep SDF. Actually, it provided us very smooth surface just by training a very minimal, very small network. And lastly, my favorite paper. I love this work so much, and I try to implement it in many different applications. Basically, the convolutional occupancy networks solves one problem. What if you have a noisy point cloud observations? And you want to generate your room, for example, and you only have the very simple and cheap Lidar that I guess the iPhones have added them to their phones, to very recent phones. And what if you want to generate your room as a mesh, a clean mesh in there? So they find a solution to this problem. And as you see in this area, they provide a very noisy, and there are some holes in the input point clouds, and the output is very clean, very neat 3D mesh object of the scene. And their application can actually provide, also can actually be applied over the whole room or independent from the dimension. So they also applied it to the whole home, for example. And this application can also be extended to the many much larger areas or regions. And also there is a Siren paper from Dr. Sisman. So there are really very, even though the applications or like the approaches may be quite small changes, but really there are amazing impacts. For example, previously in the neural networks using ReLU or Tanhash have been quite popular activation functions. However, if you replace them by using cosinus and sinus or like the periodic functions, actually it provides us the better 3D shape representation. And on the right side, as you see, the same network without changing the network complexity, just by replacing the ReLU layers with periodic functions, actually we can embed more information into the same sized network. And as far as I remember, this reconstruction has been done by using around 700 or 800 parameters only. And this is very, very, very small and simple network. And there are more algorithms and applications, and we have published a survey paper about that last year. And if you are interested in, please feel free to read our survey paper. And we also present a lot of different applications and algorithms in there. And thank you. This was all from my side. Any comments or question? Welcome.
Cool. Thank you so much, Deniz. While people are still maybe getting ready for their questions, I will start. So it's very interesting to know you mentioned that in preferred networks, you have only engineers and researchers. So how does it work? So do your researchers work on papers, they work on theoretical things, and then they give it to their engineers. Engineers try to apply this on the product? How does it work?
So basically, we have business developers along with the engineers, engineer and business developer mainly. And those people are generally working as a hybrid role between engineering and business developer and faces with the customer. But it's not only them to face with the customer. All the researchers and engineers, if they wish, they can also face with the customer. And the rest, all the remaining works like being organized or all the technical design, all the aspect is actually more like the flat organization that we have. And only last year, in 2019, actually in the end of 2019, the engineering management position had been introduced. And even before that, we were operating like only purely flat structure.
Cool.
This actually provides a lot of visibility for the end-to-end process, because while I was working in the bigger companies with like very strict organization, I could only see the module that I was working on, and I was not so much aware of the other end-to-end operations, like other parts of the structure. But working in such kind of flat organization actually allowed me to see from the contract negotiation, field delivery, and share the full responsibility is really quite a good experience.
Cool, thank you. And maybe the question that actually a lot of people here have, but they're too shy to ask. So I saw that people here are interested in the topic that you presented today, but obviously they are not in the industry yet. So what would you advise to people who would like to work with 3D computer vision, but they don't know where to start? Let's assume people already have some, let's say they have a computer science degree, or they already have some experience in programming, or maybe data science. They already know what is deep learning. So what do you think it's a best way to start getting into that field?
I see. If you had asked this question like 10 years ago, I would definitely give you the replies like multi-view geometry or some traditional ways to do that. But right now, nearly all the 3D 3D computer vision is based on the deep learning, and the traditional methods are only being referred if necessary. So that's why I would say that knowledge of the deep learning is like a must as a baseline. And then actually right now, as far as I know, there are not a lot of books or tutorials are published yet about 3D computer vision. And most of the community is followed through the academical papers. So reading the habit of reading the academical papers, I know this may be a little bit hard at the beginning. It was quite hard for me to get used to such habits at first, but this is so far nearly the only good option to dig into this area if you are interested in.
So the reading the papers, and what about the practical applications? What kind of software do you recommend to start with?
So far, actually, there is the one of the strong applications, PyTorch 3D. There is the library called PyTorch 3D, which are actually providing the off-the-shelf differential rendering applications by using software rasterizer methods. So this might be one of the library. There is also, if you want to go for the realistic rendering, there is the Mitsuba 2 rendering. And there are actually also TensorFlow provided graphics, and they also recently, I guess last month, published a new library for 3D graphics. So all the main deep learning framework providers are actually working like hard on this topic to provide off-the-shelf solutions for all the users.
We have a comment in the chat from Emil. As always, nothing in Java is possible.
Unfortunately, even though I was initially started working with Java in my first job, I really didn't see any other Java in any of the deep learning area. But I think it is possible to write a wrapper on top of that because all the major deep learning frameworks provide their C++ versions. So if you want to use the Java on top of that, you can just simply write a C++ wrapper on top of it to make it work. But if you want to train and if you want to define a model, I think there is not much other option than using Python.
Thank you. We have a question from Nabila Makhtar. Are you familiar with BTF rendering? Bidirectional texture function rendering. What are your thoughts on it? Do you think it has potential for industry applications?
Good question. Unfortunately, I don't come from the rendering part or the computer graphics background, so I'm not so familiar with BTF rendering. I'm more like the applications of the differentiable rendering on the computer vision applications. So unfortunately, I won't be able to reply this question.
Good. Nabila Makhtar, if you would like to explain more about it, you can unmute yourself and talk about it. If there is something related to the topic, feel free to go for it. Okay. Cool. We also have a question. Can you give an example that utilizes 3D CV in a commercial product, please?
Good question. Actually, the work that we did that I presented about annotating the 3D cars. Actually, it is being used as a commercial by Toyota. I guess. I hope, because this was to solve their business needs that we developed this research. Unfortunately, from the other perspective, for example, there have been some applications like just by using your camera, finding your body shape to be able to apply it in the e-commerce purposes. I think there have been some works in that, even though I'm not so familiar with that area. I guess there can be a lot of different applications, especially for the e-commerce area.
Yeah, it might be helpful for the Zodo Town. What's the name of this shop? I do remember that they have been developing the costume that has a lot of sensors, but you need to wear this costume, right, to body analyze. So this kind of technology has some potential for apparel industry.
Yeah, definitely. From now on, you don't need to actually wear any costume, but just by replacing some cameras and investing into a significant amount of processing power, it would be possible to generate the similar outputs or same quality outputs by removing all the costume requirements.
Cool. Is it possible to use this technology on manufacturing environments where there are robots interacting with people?
Yeah, definitely. Actually, this is one of the major application areas. However, the approach is still a little bit in the early phase, especially differential rendering and neural limiting functions. They are a little bit slow so far, and they require significant amount of processing power. So that's why actually PFN is investing into supercomputer. This is one of the reasons for us to invest. So far, it is mainly used to generate the labels or generate the data so that we can train another network, which can be used directly in the robotics environment or whatever the end application is. So, but I think this is definitely possible, and I think this is one of the way to follow to implement this one into robotics application.
So as I understood, this technology right now is just still emerging, right? So when do you expect it's going to be used in the more mass standards?
Well, if the acceleration was similar to the 2012 to 2015, for example, the early era of the deep learning, I would say in a couple of years. However, last year there were so many papers that I have never seen such a paper publication or paper applications in the conferences, and I was really amazed that the speed of process in 3D computer vision is moving so fast that I have never seen similarly. So that I really do expect quite a good applications within this year, or there have been already some that being worked, especially for the face part. It has been especially face recognition or single image to 3D face reconstruction services, web services. They have been already using similar technologies. So even though it's emergent as a technology, it has already started with a full force in the industry, I guess.
Do you think the pandemics was the one that triggered the technology being so active?
Most likely, or possibly, but I'm not so sure about it because this area was a little bit more silent until the Nerf paper is published. And after the Nerf paper, there have been a lot of variations, and the increase was quite exponential after this paper. So, if I would say a breakthrough, I think it was the Nerf paper.
Thank you. We have a question. I'm sure you have touched already, but would you show us any actual applications of this? Hopefully ones familiar to us, to the development of services or products by business companies.
Good question. One of them is, for example, PFN is developing the manga colorization technique. So one of our teams are actually colorizing the mangas just from the scratch, and whichever the color scale that you want. Actually, this technology is being used in that part, and this is one of the commercial applications that I can give as an example of.
Are you hiring? Are you hiring? If so, how should I get in touch?
Well, as far as I know, I guess we started hiring about the fresh graduates, but I'm not so sure. So please follow our career page. If the applications are open, we will immediately show it in the career page.
Do you think there's a typical profile of people who are getting into preferred networks for engineering or researchers positions?
Yeah, we generally hire 2 or 3 types of people. Either you have a very good business knowledge about how the deep learning and its applications can be applied as a product. So you can enter as for business paths. But in general, you either need to show a very good engineering outputs, and the GitHub open repositories, your works as a student are an amazing way for us to elaborate you as a possible candidates. Or what we would like to see is some publications, possibly in the top conferences in the world. So this is the kind of minimum criteria to go into PFN. For example, I didn't have any publications until I joined here, but I could show some kind of engineering work and my previous applications, and this was how I ended up in PFN.
Cool. I just sent a link to your careers page. Those who are interested. So the careers usually 2 types: engineering and research. So those who are interested can take a look. Cool. We have just 2 minutes left until the end of the workshop. So if you guys have any last questions, feel free to shoot them. Otherwise, we'll wrap up the talk. Deniz, maybe the last question. Rodrigo, has any Levagon graduate ever gone to work at preferred networks? No. That's such a high level. So I'm pretty sure that we need to have our advanced bootcamp hour after data science bootcamp in order for people to get ready for the preferred networks. But yeah, that's a goal. Cool. Another question: having a different background, for example, degree in Electronic
Electronics
engineering. How do I get a job in computer vision? Is it possible if one doesn't have a paper certification degree?
Yeah, definitely. I'm an electronics engineer. Actually, I have the master's in electronics engineering. It does. You don't have to be a graduate in computer science. We also have some graduates from the physics. We have graduates from the mathematics. We have graduates from different areas. So your title, your university title, isn't actually such an important detail for us. But the works that you do as a student or as a professional, this is what we are mainly focusing on. So basically, we care what you know. And especially about having a degree in electronics engineering, the path that I followed was I did my master's in image processing and as a, under the electronics engineering. So which led actually me to learn by myself to deep learning so that I could ended up in PFN. So, but the experience that I took from the master's degree was the traditional one, and I was not aware of the deep learning or such technology at the time. So that's definitely possible through the self-training and personal hard work.
Oh, that's very inspiring. Thanks so much, Deniz. Yeah. Economic degree holder here. Emil guesses only hard work can help us to go through the process learning. We will see in the future how it will go. Definitely, as Deniz mentioned, there are a lot of work should be done, and something that you can start with. As I said, in our community, we have people a lot who are doing the web development, who are doing the data science. I think this is a good start. At least the data science bootcamp is also the good start. And then, of course, maybe a couple of publications would be good to get you in the preferred networks. Is it correct, Deniz? Is publications necessary or like preferred?
Again, if you want to come as a researcher, definitely some kind of publications will be really helpful. But there is also the engineering paths, and we do require the good engineers in here, even though you don't have publications like me before joining PFN. If you can show the good engineering work, if you can have some kind of experience in the good engineering work, this is also possible to come and work with us.
Cool. Is there any computer vision meetup group in Japan?
I hope there is one, not that I'm aware of.
Yeah, I'm pretty sure Machine Learning Tokyo might have some kind of community. But yeah, you guys definitely, I'm encouraging you to start one. You can have Deniz as a team leader for the first couple of sessions and then continue to learn. If there are any resources that Deniz you can recommend for people who would like to get into the field, I think people will really appreciate. If there are any like websites or like some like something that people can start with would be really cool. Or some communities, maybe there's a Discord community or something like that.
Again, not that I'm aware of, because my work is mainly either reading the papers or digging into information that I need from the internet, rather than following an open source community, because we already have the PFN community is a private area that we can share a lot of knowledge. So that's why I'm not so familiar with third-party applications, but I do recommend to follow up the mainstream deep learning frameworks and their publications like PyTorch 3D, because generally they follow up the latest trend in the academia, and they bring the good engineering to the everyone.
Cool. Thank you so much, Deniz. I think that's time for us to wrap up the event. Thank you everyone for joining and staying with us until that long. As just summarizing the piece of conversation, I encourage you to start your own group. For those who are interested, maybe you can reach out to Deniz after the event. You can find him on LinkedIn, just using his name, and feel free to ask him a question about that, and maybe organize some community that would be really cool to have.
Sure, it will be really amazing.
Cool. Thank you so much again, Deniz. It was really good. Thank you for your time. Thanks for an amazing and very informative presentation. Thanks, everyone. Feel free to follow Wagon Meetup group for more cool events coming, and have a great evening. See you next time. Bye.
See you. Have a nice day.
Oh, yes, definitely. You're in Turkey, so have a nice day.
Oh, yeah. Have a nice day for me. Yeah. Bye-bye.
Bye.